Okay, hi, I'm Frank McBride,
Uh, Hi, I'm Catherine Yu.
Hi, I'm Joshua Wassenaar.
and we're going to be presenting wearables with low power applications. The first thing we're going to discuss is a new protocol called WAKA, which is to be explained later. WAKA stands for Wearable Assisted Continuous Authentication. Now, what this does is it proposes a novel sensor-based wearable assisted authentication framework. Proposes a new variant of keystroke dynamic tracking and illustrates the robustness of the method against various attacks. Now, what this means is, in basic, a wearable is worn by the user in order to perpetually authenticate the user by modeling their typing habits. Why would this work? So through experimentation, it was found that different users exhibit different patterns while typing, exclusively different patterns while typing. Previous work was able to ascertain passwords using the accelerator of a phone. This was more of a malicious and bad technique that was being used, but it does end up having positive outcomes. Among all biometrics, it's the most promising results being keystroke dynamics because it's cost effective. It's also not intrusive, like for instance, a retinal scan would be. And when they did the biometric studies, they found that, as you'll see in the next slide, that the Z-axis keystroke features is what really differentiates one person from another, which would be the up and down for those who are forgetting quickly the Cartesian plane. So if you see, we have the wearable in a typing position. We have the y-axis would be frontwards and backwards, x-axis side to side, and z-axis upwards and downwards. And on the right-hand side is a function of time that has the raw data being the z-axis and actual keystrokes being identified by the red dots. This is a comparison using the accelerometer and the gyroscope readings from the same wearable and same text being typed, but two different users. And you can see how there are differences in the gyroscopes readings, but they are not as drastically different as the accelerometers in differentiating between the two users. So it has 4 stages. Those are pre-processing, feature extraction, user profiling, and the decision module. The first one is the pre-processing. So what that does is it refers to the preparation of raw sensors readings for the next stages. Now what that means is it actually just takes, it's like when you use the Face ID on a phone, it takes multiple readings in order to get a feel and understanding of what your typing dynamics are. Once that's done, it needs to filter out a lot of noise in order to create the profile, which is done in the process of feature extraction. It filters the noise, the data is transformed into appropriate forms for the next stage, and there's a lot of vector math involved, but basically a vector is created for each user as a function of f. Once they have created all these functions, there's a profile created. And it's coupled with a user ID, a start and end timestamp, and the data sample that was used in order to take the readings in the first place. If you look down, there's a table of all the readings that were taken. And finally, the decision module. So what that does is, on a continuous basis, whenever typing is being done on a computer. It takes the user ID that was referred to before and compares it to the authentication that was done in the first place. So this program assumes first step authentication has been performed. This is a perpetual second stage authentication process. As you can see here, that there were multiple different types of distance that they could have used. Within the paper, they actually describe the results that were given by the different distances, like cosine distance, correlation distance, and Minkowski. But they ultimately went with Euclidean distance, as it was the simplest and most effective. So this is an overview diagram, finally, about how the program works. So I'm going to try to use my cursor here. And so in the first place, a typing notification is sent from the computer to the wearable device, where pre-processing is done on the typing readings that it's done. And it takes the feature extractions, which is another word for removing all the noise, compares it to the user profile, and sends it to the authentication server. After that, it is sent over to the decision module that determines whether or not the feature extraction matches the user profile. If it does, then it goes back and, if it doesn't, it goes back to the authentication server and sends an update that it is not valid. And if it is valid, then it is automatically relogged in.
Okay, so I'm going to be talking about LoRa, which is basically long range. And so basically, what is LoRa? LoRa is a new physical layer using chirp spread spectrum, which is CSS, that was designed by Semitech Corporation, and is basically a star network and can cover a few kilometers using a high gain antenna. Since it only consumes 0 to milliamps in sleep mode, it could be able to achieve long-range communication with low power consumption. So basically, why is LoRa important? It's important since wearable sensor nodes are generally deployed in medical environments to monitor the biological information from the human body and transmit over a short distance to a gateway or control unit via a wireless network. In addition to medical applications, wearable technologies can be used in safety monitoring, for example, in construction safety applications. Because these wearable devices are worn on the body, they need to be lower powered, miniaturized, and can detect multiple environment conditions. Since collected environmental data needs to be transmitted to a gateway node via a wireless network, XB was a suitable option as it was low powered and can cover a relatively long range, which is around 100 meters, and use Bluetooth. Bluetooth is widely used in wearable body area networks for medical application. However, it can only cover 100 meters, like I said before, compared to LoRa, which goes over a couple of kilometers. Okay, so this picture basically shows like an experiment of the distance how LoRa of one LoRa node can cover around 500 meters. So this one LoRa network is able to cover half of a campus, and in the picture they're using in the previous picture they were using a microcontroller unit with multiple sensors and a wireless module on the sensor node. So they basically used, from the experiment, they used the AT-Mega32AP, so the microcontroller can communicate with different sensors and the wireless module. It also controls a load switch, which was a TPS22908 on or off that provides power for different sensors. It also consumed low power and has high performance and low cost features. 3 different sensors are also used in this work, which were temperature, relative humidity, and UV sensor. The temperature and relative humidity readings were achieved by a low power and accurate sensor, which was the BME680, and the UV data was acquired by the SI1145 from the Silicon Labs. So the extreme hot temperature or the humid weather may cause effects on the physiological responses and result in heat illnesses. and the excessive UV exposure will cause sunburn. Therefore, it was important to measure temperature, humidity, and UF in safely related applications. And the long-range LoRa wireless connectivity was achieved by the RFM95. And so it had a low current of 10.3 milliamps and only consumed 0.2 milliamps in sleep mode. And the network topology, again, was the star network, and all the environment data monitored by the sensor node was transmitted to the gateway directly. In this picture, this is how it would look like, how it looked like. They have the energy harvester, the LDO, the switch, the onboard sensor, the MCU, and LoRa, which was here. And I'm going to give it to Joshua for the glove type.
Joshua, I'll be presenting the third article, which is glove type of wearable tactile sensors produced by artificial hollow fiber. One of the struggles of designing wearable tactile sensing devices is the flexibility of the sensor structure itself. A sensor often cannot bend or flex without breaking due to its physical structural design. There are some ways to remedy this problem, and this can be done with materials such as polyimide film, but these can still only bend along one axis. This would work well with a cylindrical surface, but not with the fabric of clothes. In order to design wearable tactile sensor clothing, they need to be even more flexible than this. They need to be able to flex and bend like a fabric does in clothing, all while being able to still be an accurate sensor. The paper proposes an artificial hollow fiber structure to make a sensor that is flexible enough to be a wearable tactile sensor. This artificial hollow fiber is flexible enough to be incorporated into clothing seamlessly. It would enable us to wear tactile sensors and incorporate them into everyday clothing. This artificial hollow fiber is made of commercially available silicone rubber tubing, making them cheap and easy to produce. In this case, the sensors are being incorporated into gloves. According to the article, the sensor is produced by weaving the hollow fibers together. The applied contact force is detected by measuring the change in capacitance between the warp and weft fibers at their intersection points. When a load is applied to an intersection point of the fabric tactile sensor, both the warp and weft fibers deform. As a result, the capacitance between them increases as the applied load increases. Therefore, the sensor can detect the contact force by measuring this change in capacitance. There are two kinds of fabric tactile sensors that have been developed. The first being the patch type, a rectangular shaped fabric tactile sensor that was made by combining the artificial hollow fibers in yarn. This kind could be patched into a commercial glove using yarn. The second kind is a direct knit type. The artificial hollow fibers were woven directly into the glove yarn instead of being patched on. With these two kinds of fabric tactile sensors, already existing clothing could have them easily patched on, and further clothing designs could have them implemented directly into their fabric. With this kind of fiber tactile sensor technology, we can incorporate these kinds of sensors into everyday clothing. This can be used for many applications, such as in an IoT network. They would be easy to implement, cheap to manufacture, and require very little power. These kinds of wearable sensors could have countless applications and opens a whole new world of opportunity to seamlessly implement sensors into everyday life. And to wrap up our presentation, thank you for watching, and here are our references.